meeting when recording starts. Chris, Larry. Chris, can you hear me? Okay, so he will
Yes, sir.
probably have to join in again.
Yes, sir.
Okay, you might get removed from the Google Meet. Okay, you just have to join again. All right. So that's the message which I got from Google Meet. Okay. If in case you get removed, just join in again. All right. Okay. So this is
Okay,
where we
sir.
had stopped in the previous class, right? Cauchy integral theorem for multiply connected domains, and then I had asked you all to try this out, right? So I hope you all have done this. All you have to do is just you have to make some cuts here. That's all. Okay. Make those cuts, and that is going to you can just apply the Cauchy integral theorem. No, not this. I think this was it. It was on 8th of December. I think, and this also here. On 8th of December, we had our last class. And today is 14th, I guess. Okay, so yeah, this is how you're supposed to. This is how you're supposed to. Did I provide you with the slides? Did I provide you with these slides? I don't think so,
Yes,
right?
sir.
So I'll provide these slides. Okay, I'll provide these slides
Sure.
today. Okay, I'll provide these slides here. So this is how you have to actually prove this. Okay, and it's very straightforward. That's your Cauchy's integral theorem. Okay. Okay, so next is Cauchy's integral theorem for multiply connected domains. Okay, next we have the Cauchy's integral formula, very important formula, especially for net exam. Okay, for net exam problems on the Cauchy's integral formula are very common. Okay, so what it says is this. Okay, so suppose I have a simply connected domain. Okay, I have a simply connected domain D. And inside this simply connected domain, we have a simple closed curve. That simple closed curve is C. Okay. Then the integral of not the function. Let's say f is an analytic function. F is analytic in this region. In fact, f is analytic everywhere within this region D. Okay. Then the line integral, the closed line integral of f divided by z minus z naught is equal to twice pi I f of z naught. Okay. So now it's a little bit tricky to understand. Let's just go to the whiteboard and see how this works. Okay, so what we have here is this. Let's start with the Cauchy's integral theorem. Okay. Okay, I have a little bit of problem with writing on white background, so I'm going to use a black background. Okay. My handwriting gets spoiled when I write on a white background. Cauchy's integral theorem. Okay, as per Cauchy's integral theorem, what we have is this. So suppose I have some domain. Okay, let's say this is some domain. This is some domain D. All right, and let's say this domain D is just filled up. Okay, so this is our domain, and within this domain, the function f is analytic everywhere. So this is our domain D. The function is analytic everywhere. Okay, so now if suppose I take a curve, a closed curve here. Okay, if I take a closed curve, if I take a closed curve, okay, let's say this is the closed curve. The curve is C. The Cauchy integral theorem, what it says is there is if, okay, this function f of z is analytic, is if the function f of z is analytic on D, okay, then as per the Cauchy's integral theorem, the line integral, the closed line integral over C of this function f of z dz, this will be equal to 0. Okay, so that's your Cauchy integral theorem. This we already know, right? Now let's consider a point here. Okay, just copy the whole thing. Okay, now for Cauchy integral formula. Now let's look at the Cauchy's integral formula, because this could be a source of confusion. Cauchy integral theorem and Cauchy integral formula. So what the Cauchy's integral formula says is this. You see, the same condition, same holds good. Okay, f of z is analytic if f of z is analytic on D. That we already know. Okay, f of z is analytic on D. But now there is a point. Okay, let's say a point which lies inside C. Okay, let's say there is a point over here which lies inside C. And this point, let's say we call it as z naught. Okay, this point we'll call it as z naught. Then let me write down another function. Okay, I'll write down another function. That function I'll call it as g of z. Okay, g of z. And how I define this function? I define this function in this way. I'll take the original function, that is f of z, and this original function I'll divide this function. I will divide it by z minus z naught. Okay, now you tell me, is this g of z? Okay, we'll define it like this. Define it like this. Now you tell me, is g of z, if g of z also analytic over D? Look at the diagram, look at the expression and tell me. Can anyone tell me? This G I have defined it this way. So is G also analytic over this D? Who can tell me? Anybody? Is G also analytic over D? What is the definition of analysis D? Anybody?
Sir,
Yeah.
becomes infinite at z equal to 0.
I am not able to hear you. Who's speaking?
It becomes infinite at z equal to z naught.
Is it urban? Is it urban?
Yes, sir.
Okay, can you speak louder? I'm not able to hear you. Your volume is very low.
It becomes 0 at, or it becomes infinite at z equal to z naught, sir.
Yes. Yes, it becomes infinity at z equals z naught. So because it becomes infinity over here, that means G is not analytic everywhere. Very good. The answer is no, of course. The answer is no. Okay, because because since G of z is undefined, at z equals z naught. Okay, so because this is undefined, G of z is undefined, so G is not analytic. So therefore, from the Cauchy's integral theorem, therefore, from the Cauchy's integral theorem, okay, from the Cauchy's integral theorem, this is not valid because the Cauchy's integral theorem says that only if the function is analytic, this closed loop integral will be zero. Okay, so as per Cauchy's integral theorem, the closed loop integral of g of z dz, the closed loop integral of g of z dz, this will definitely not be zero. Okay, so if g of z dz is not zero, that means what is g of z? G of z is f of z minus z by z divided by z minus z naught. So this means integration over c, g of z is nothing but f z dz divided by z minus z naught. Z minus z naught. This is definitely not zero. Is that understood? Is this understood? So is there a difference here? The difference here is this. F is analytic. F is analytic. Okay. So F is analytic. So this is true. But f of z minus z naught is not analytic. So this is also true. That means integration of f over c is zero, but integration of f divided by z minus z naught, that is not zero. Okay. So what is it? If it is not zero, then what is it? The Cauchy's integral formula, it gives us the answer. Okay. So if this is not zero, then what is it? The Cauchy's integral formula, okay, according to the Cauchy's integral formula, okay, this integral, that is the closed loop integral of fz dz divided by z minus z naught, this is non-zero and it will be, its value will be equal to 2 pi I into the value of this function f is analytic everywhere. So f is not undefined at z naught. G is undefined at z naught, but f is not undefined at z naught. So just find out what is the value of f at z naught. So twice pi I into f of z naught. So that is your Cauchy's integral formula. Okay. So this is what it says. So as per the Cauchy's integral formula, f of z divided by z minus z naught into dz, the closed loop integral of this is going to be equal to twice pi I into the value of the function at z naught. Is this clear to everyone? Is this clear?
Yes, sir.
Yes, sir.
Okay, so now we can prove this. We can go ahead and prove this. Okay, so even if you don't understand the proof, no, even if you don't understand the proof, but if you understand this idea, okay, what is happening here, then that is enough for you to solve problems. In net exam, that is enough for you to solve problems. Okay, you don't have to worry too much about this. But for our exam, we have to know the proof. Okay, the proof of this. So f is analytic everywhere, but f divided by z minus z naught is not analytic at z naught. Okay, so f is not an f of z minus z. F is analytic. Sorry, fz is analytic. Fz is analytic here. Okay, fz is analytic, but fz divided by z minus z naught, at the very same point, it is not analytic. Okay. So what we can do is this: we can use the principle of deformation. Remember the principle of deformation? The principle of deformation, what does it say? It says that I could just change the path. I could just change the path as long as all the points, they always remain within the region where it is analytic. Okay. So let's say I want to integrate from point 1 to point 2. I could go from point 1 to point 2, point 1 to point z1 to point z2. I could go from z1 to z2. And I could go from here by changing the path. I could keep on deforming the path, changing the path like this by smaller amounts, as long as the path always remains inside D. So same thing here. I could go from z1 to z2 like this. Okay, I could go like this, but I cannot go straight here because I cannot deform this path. Okay, I cannot deform I cannot deform this path. This path, I cannot deform it and make it a straight line, because if I make it a straight line, it will pass through some regions which does not lie in this region. The function need not be analytic, so I cannot deform it like this and make it straight line. But in this case, I can do that. I could continuously deform this path and make it straight line. Okay. So what does this actually say? It says that if you can deform the path, okay, if you can deform the path that we have here, because I'm allowed to deform the path here. So again, let's say I take this domain. Okay. So I have some domain. This is some domain D, and I'm having some path. Okay. Some path is there. This path, I call it as C. I can always deform this path. I could change this path, because you see all the points, the only discontinuity is at Z0, right? The only discontinuity at Z0. So this path, I could change this. Okay. Gradually, I could change this path. Gradually, I could change this path and I could convert this path into a circle. Okay, this path, I could convert this curved path, C that we have. We could gradually change this path, we could gradually deform this path, and I could convert this into a circle. Okay, I could go on changing this path, keep on deforming until you reach until it becomes a circle. This is allowed because the only discontinuity of f of z minus z, f of z divided by z minus z naught, the only discontinuity is over here at z naught. Okay, so as long as the path does not cross z naught, I could keep on deforming it the way I wanted. So I keep on deforming it, and I can as well just make it a circle. Doesn't matter. The integral over this path and the integral over this circle is going to be exactly the same. From the principle of deformation, we know that this is indeed going to be the case. So this is what we do over here. Okay, so we will deform this and we convert this path into a circle. Okay, the center of the circle, we take the center of the circle to be at z0. The center of the circle, we take it to be z0, and the radius of the circle, we call it as, let's say, rho. Okay, we can do that. We are allowed to do that. Okay, so now this is what we have. Okay, so now we again go back to the definition of analyticity. So since f is analytic, it is also continuous. And if a function is continuous, again go back to this, right? This is how we define continuity, no? So if you give me an epsilon, you give me an epsilon, I can always give you a delta, such that, okay, in the disk where z minus z naught is less than delta, the value of the function, the difference in the function will be less than the epsilon that you give me. So you give me an epsilon, I give you a delta, so that within this disk of radius delta, the points that I take, the functions that it will give, the difference in the function will be less than your epsilon. So if I can do that, then that means it's a continuous function. Okay, so this is what we have. I go back to the definition of a continuous function. So if I choose the radius of C, okay, if I choose this radius of C, that is rho, if I make it smaller than delta, okay, rho if I make it smaller than delta, then f of z minus z naught divided by z minus z naught, this quantity is going to be less than, epsilon by rho. Okay, it's going to be less than epsilon by rho. Okay, epsilon by rho here, because you see f of z minus z naught is less than epsilon, right? F of z minus z naught is less modulus f of z minus f of z naught, this will be less than epsilon. So this entire quantity, it will be less than epsilon by rho. So we have in this expression, again we go back to this integral f of z by z minus z naught. We open this up, so we just add and subtract f of z naught. So f of z plus f of z naught here, and we have a minus f of z naught here. No harm, we can do that. So then we get two integrals. Okay, two integrals. One integral will be this. Let me write this down over here. So this one, we'll get two integrals. Okay, so one integral will be this one, f of z naught, right? One will be an integration of f of z naught, integration f of z naught, divided by z minus z naught. Integration is over c. Then another one will be, the other one will be the rest of the two. So integration of over c, f of z minus f of z naught divided by z minus z naught into dz. Now here f of z is a constant, no? Because it's the value of the function at the central point. It's a constant. So because it's a constant, it is going to come outside the integral, and that's why we have this outside the integral. So these two integrals, the first one, f of z naught, comes outside, and we have this. What is left behind is dz divided by z minus z naught, and we have this one, this other integral. So now you can actually get an idea of where I'm trying to proceed from here. Can you see? Remember this integral? Integration dz by z minus z naught to the power n. Remember this? What was the result that we got? Does anybody remember? What was the result that we got? Or rather
2
like
pi I
this.
for n is equal to minus 1.
Yes, actually we wrote it like this. We had written this like this. Okay, integration of z minus z naught, z minus z naught to the power n into dz. It has got two kinds of values. The first one is it will be 0 if n is not equal to minus 1, and it will be equal to 2 pi I if n is equal to minus 1, right? We have these two values. So n equal to minus 1. So if you put n equals minus 1, so we have integration of dz minus 1 is 1 by z minus z naught. So this result will be equal to 2 pi I. So we already know this. This result will be equal to the result of this integral. This particular integral, the first integral that we have here, the first integral, this one's result will be equal to 2 pi I. Okay? And already there is f of z naught. So this f of z naught is there, and there is a 2 pi I here. So together it will give me 2 pi I. And this is what we have in the Cauchy integral formula, right? 2 pi I into f of z naught, right? 2 pi I into f of z naught. This is what we have. And then here the first integral, it is going to give me 2 pi I into f of z naught. So what we need to, what is left for us to show, what is left for us to show is we have to show that this will go towards 0. Okay, this will go towards 0 as epsilon tends towards 0. If we can show it, if we can show that this integral goes to 0 as epsilon tends to 0, then we have proved the Cauchy integral formula. Is that clear? Because the second term, if it goes to 0, what will be left behind is only 2 pi I into f of z naught. Is this clear?
Yes.
We have to basically show that this will go to 0 as epsilon tend to 0. So how are we going to do this? How are we going to do this? How are we going to show this? What method are we going to use? Can you take a guess? We are going to use a result, okay? A very important result which we discussed in one of our previous classes. Anybody? By what is known as, remember this, ML inequality, right? We're going to use ML inequality again here. You can use ML inequality to make anything, any integral. You can just make its value to be, its integral value, you can make it to be equal to 0. So we just use ML inequality and we show that as epsilon tends towards 0. So basically you have to show that this integral, the modulus of this integral is less than epsilon, which you have already seen over here. So as epsilon tends towards 0, then this is also going to go towards 0. So if you can do that, then our problem is solved. Is that clear? So that's what we will do next. Okay, so these are the two equations that we have using the ML inequality. That's what I said. We already saw that this integrand, the value of this integrand, okay, this integrand, the value of this integrand, if you take the modulus of this, okay, that modulus is less than epsilon by rho, right? So remember the ML inequality. What does ML inequality say? ML inequality says that, so if I have f of z dz, and which is integrated over c, and if the function, the integrand, Okay, this if the integrand is less than some value m, and L is the length of the path of integration. If L is the length of the path, then this one's is going to be less than m into L. So that's your ML inequality. And we already have the integral here. What is the integral? Integrand? Integrand is this ratio, f of z minus f of z naught divided by z minus z naught. So this is the integrand. So using ML inequality, this integrand value, we have already seen that this is going to be less than epsilon by rho. Okay, it's less than epsilon by rho. And we are taking integral. We are taking this integral over one closed loop, right? We are taking this integral over one closed loop. So this is the integration path. Which is the integration path? This one is the integration path. This is the integration path, right? So we already know what is m, right? We already know what is m. What is m? M is this quantity, the integrand. What is the maximum value? M is epsilon by rho. Then what is L? L will be the length of this path, right? What will be the length of the path? This is a circle, no? This is a circle. So what is the length of the circumference of a circle? Length of the circumference of a circle is 2 into pi into the radius, which is 2 into pi into the radius is rho. We have chosen the radius to be rho. So m is epsilon by rho, and the L is 2 pi into rho. Okay. So that's what we substitute over here. So this is your m. This is m and this is L. So m into L. So over here rho gets cancelled. So what is left behind is 2 pi epsilon. Okay, it is 2 pi epsilon. So you can see here this entire quantity, this integral is less than, there is a less than sign here, this entire integral is less than 2 pi epsilon. 2 pi is anyway a constant, so we can say that this integral is less than epsilon. Okay, so if we can choose epsilon to be arbitrarily small, if we choose epsilon to be as small as we want, the last integral can be made 0. If I choose epsilon to be 0.000001, then the last integral will be even smaller than that. So we can set the last integral to 0. And once we set the last integral to 0, only the first integral remains. And this result we already know. That result is equal to 2 pi I. So this gives us the Cauchy's integral formula. Okay. So this is the Cauchy's integral formula. Is this clear? Everybody? Any questions? That's the proof, okay? That's the proof of the Cauchy's integral formula. So now let's just quickly apply the Cauchy's integral formula in some example problems so that you get an idea of how this works. Okay, so let's consider this problem. The problem is you have to integrate e to the power z by z minus 2 for this one. So let's go ahead and do this. Let me just copy this problem. Give me a second. Okay, so this is what we have. Then let me draw the this one complex plane, so we get an idea of what we are dealing with here. So I need a circular path because this is a circular path that we have considered here. Okay, so this is a circular path. Okay, so what is C here? This is C. Okay, this is the path C. Okay, so we have to consider two paths. One is when modulus Z is 1. Okay, so C, the first case, that is, let's say case A. Case A, C is such that modulus Z is equal to 1. Modulus Z is equal to 1 means it will be the circle whose radius is equal to 1, right? So this is basically a circle centered at the origin, a circle centered at the origin, and with a radius of 1, and with a radius of 1. Okay, by the way, in general, no, this is how we can represent a circle in general. Let me just write this here so that you can keep this in mind later on. So in general, this is just a side note. Okay, this is just a side note. So in general, if I write something like this, okay, if I write something like modulus z minus z naught, modulus z minus z naught is equal to, let's say, some r. Okay, so this is it represents a circle, represents a circle which is centered at z naught and has a radius of r. Okay, so basically like this. So this is the, let's say, the complex plane. So we have a circle whose center is at z naught and whose radius is r. So you could just represent it in this way, in this form. Okay, so here, if you consider this, so z minus z naught is less than r, z minus z naught. So this can be written as, z minus 0 is, okay, so this is inside, no, just a second, not less than, this will be equal to, because you're talking about a path, not a region. Okay, all right, so this is what we have. So this gives z minus 0 is equal to 1. So immediately we know that z naught is 0 and the radius is 1. So here we are talking about a circle, whose center is at the origin, and whose radius is equal to 1. So this is what we are talking about. Okay, so now let's look at the function here. The function is f of z, which is equal to e to the power z. This is analytic. This is analytic everywhere. Okay. This is analytic everywhere, right? It is analytic on C and it is analytic on, everywhere on C, right? So it is analytic everywhere. Okay, but f of z, okay, divided by z minus 2, which is equal to e to the power z by z minus 2. This one is not analytic everywhere, is not analytic is not analytic at z naught equals 2, because if I put, at z equals 2, because if I put z equals 2 here, 2 minus 2, this is going to give us undefined result. Okay, so this is not analytic. This function is not e to the power z is analytic, but e to the power z by z minus 2, this is not analytic at this point z equals 2. So how do we evaluate this? We can just use the Cauchy integral formula. Okay, or the Cauchy integral theorem. You can just use that and we can just have a look. All right, now where is this point z equals 2? Where is the z equals 2? So now if this is the origin, because this radius is 1, so this point must be 1 and this point must be 2. This point must be 2 here. Okay, so this is the point which we have considered. So now in the first case, in this case, let me write this down below. The first case is this. Okay, so this is what we have here. Now, e to the power z by z minus 2 is analytic everywhere inside C, right? E to the power z, e to the power z by z minus 2, this function is analytic everywhere inside this C. Okay, why is it analytic everywhere inside the C? Since this z equals 2 lies outside, right? Z equals to, it lies outside C. So because Z equals to lies outside C, so therefore we don't have to use the Cauchy integral formula. We can just use the Cauchy integral theorem. So by Cauchy integral theorem, we have the Cauchy integral theorem. We have over C, okay, e to the power z by z minus 2 dz. This will be equal to 0 for C such that modulus z is equal to 1. So the first case that we considered, the first case over here, the first case, okay, this integral, okay, it is going to evaluate to 0. Okay, but if I look at the other case, the second case, the case B, in the case B, the C, the path is chosen such that modulus of z is equal to 3. Modulus of z is equal to 3. Okay, so again, this implies z minus 0 is equal to 3. So here the center is at 0 and the radius is 3, right? So now if you again look at this, if you again look at this, at the same thing as before, the same diagram as before. Let me just get these points a little close. 2 is here and 3, let me just get this slightly closer. 2 is here, 1 is here, and 3 is here. Point 3 is here. Okay. So earlier this was the circular path, right? Yeah. This was a circular path of radius 1, but now the radius has become 3. The radius has increased now. The radius of the path, it is no longer 1. The radius of the path is 3. This is the radius of the path. Okay. So this same path, this new path, okay, the new path C, this is C, this is C. The radius of this path has now become 3. Earlier it was 1, now it has become 3. And now we notice that there is the singularity, the discontinuity that we have, no, the singularity, it lies inside C now. Okay, it lies inside C now. So with this, okay, over this, here, oops, here, e to the power z by z minus 2 is not analytic at the point z equals to 2, z not equals to 2 inside C, z not equals to inside C. So what do? We have to now, do the deformation of the path. Okay, we have to deform this path. So take this same path as before and now you deform it. We deform it and make it a smaller circle so that, that circle becomes a new center, right? So we deform this and form a smaller circle. We keep on changing the shape of this until we get a smaller circle which is centered at 2. Now I got a new path here. This is a new path. This new path we'll call it a C prime. I could keep on deforming this because the points they're always lying inside the region where it is always analytic. So I could always do that. So now this point becomes your Z naught. So all you need to do now is just check. In the first case, just check, find out where is the discontinuity, find out where is the singularity. The singularity is a 2. First case, 2 was lying outside, 2 was lying outside the contour C. So the result, we can just directly use a Cauchy integral theorem, CIT, and that gives us a result 0. So if the singularity lies outside, it will give us 0. But now the singularity lies inside. So I use deformation of paths to get another circle here, such that the singularity is the center. So we see that we can apply the Cauchy integral theorem in this case. So here, by Cauchy integral theorem, we have the Cauchy integral theorem over this path C, e to the power z by z minus 2 into dz. This is equal to 2 into pi into I into the value of the function. Which is the function? Remember, this is the function, okay? This is your f of z, not f of z by z minus 2. F of z minus z minus 2, that is not the function. The function is whatever is there in the numerator. So whatever is in there in the numerator, which is e, okay, what we need to do is we need to find out the value of the function at z naught, and here z naught is equal to 2. Z naught is equal to 2. So this will be equal to twice pi I into the function is e to the power of 2. Okay, so this, when you evaluate this, approximately e square, if you evaluate this, the result will turn out to be something around like 46.3 I. Okay, this is the value that you will get. So this is the integral. So over the first part, this will result 0, and over the second part, its value will be around 46 I. So that's how you solve problems like this using the Cauchy integral theorem or the Cauchy integral formula. Okay, so I'll give you another problem, a couple more problems. So please try these at home. Okay, so this one, okay, f of z, the first one, integration of z cubed minus 6 by 2z plus I over this contour, and the last one is this function z square plus 1 by z square minus 1 individually over all of these 4, c1, c2, c3 and c4, or all of these contours. Find out what will be the integral of this. That means this problem, there are 4 parts to it. Okay, this problem, there are 4 parts to it. That is, we need to find out the integration of g of z. We need to find out integration of g of z over c1, integration over c2, integration over c3, and finally integration over c4. All 4 you have to find out. Okay, these 4 you have to do. Is that clear? Can you all try this?
Yes, I will try.
Okay, so let me provide this. I'll give this slide so that you all can try this out. I'll provide you with the this one, whiteboard, and you can just try it at home. Okay. So the next is Cauchy integral formula for derivatives. Okay, for derivatives, but this is a general formula. The proof is not required. Okay, the proof of this, but still I have given the proof here, even though in the this one syllabus, the proof of this is not required. Okay, for derivatives, I gave this proof, I think, because last year, you know, in your seniors, some students were curious about this, so I gave the proof. So maybe let's see how much is left. Yeah, because you just need to know the application of this one. Okay, so I'll do one thing. I'll give you these entire set of slides, all these slides. Okay, the whole slides, because this is the last slide. Okay, this one is the last slide. This one is the last slide. So till here. Okay, so I'll give you this this entire set of slides. What I want you to do is just go through this proof, the second one. No, that is for derivatives. No, derivatives, this theorem, the proof. I want you to just go through this proof, see if you're not able to understand this. If you feel that you're not able to understand how we got this proof, yeah, how we derived this, then maybe I could just quickly go through this and show you how I did this. Okay. So in the next, but I'll show you the application. Don't worry about that. The application I'll show you how to apply this in such problems, that I'll show you. So with this, maybe like I could consider this particular topic to be done. Okay, complex integration. Next class, in case you want me to just go through this proof, I'll do that, and maybe one or two problems we'll do. That is tomorrow, and then we will move on to the next topic, which is complex series. Okay, Taylor series, Maclaurin series, all these different series representation of Lorentz series, and Maclaurin, this one, all these series expansions of complex functions. So those we will have a look in the next class. Okay, if you have any questions, you may ask me now. Any questions? Okay, so if there are no questions,